What's going on? My name is Anastasio Dalde. This is SDG Labs, and I just screwed up that introduction. In 2011, Aroldis Chapman fires at McCutcheon with 105.96 mile an hour fastball. I think that is the to date fastest recorded official Guinness Book of World Records time for a fastball, which is pretty fast. All right, check out the video here. Blah blah blah. You can watch it. All right. How long does it take for it to reach the catcher's mitt after it left the pitcher's hand? Okay, so here's what I'm going to do is I'm going to kind of draw the little man here, and I've got the catcher's mitt, and then I've got the, well, here's the catcher. He's crouched down. He's not really that short. He's just crouched down. And this dude shoots the ball out at a velocity of whatever, and it reaches the catcher's hand, and so there we go. So if I want to figure out how long it takes, I have to know the distance in between here and there. And so the distance is, I don't know, that's something I can look up. I'm actually not going to solve this problem, this homework with any numbers. I'm just going to do the variables because I want to really kind of see the pure physics of it all. Anyway, here we go. V naught x is equal to distance over time. So if I want to figure out what time it is, all I got to do is solve for t. Therefore, t is equal to distance over v naught x. There we go. All right. Now here's another question: is how far did it fall in the amount of time that it took? Okay. Well, this is part B. The amount of time that it took was this. How far did it fall? Well, we would simply use this equation. I know that the velocity initial in the y direction is 0. I know that the acceleration is negative g. I know that the, let's make it delta y is what I'm looking for. And also the, I know that the time is equal to d over v naught x. That's right from there. So the equation I would use is probably delta y equals v naught t plus 1/2 at squared. Delta y is what I'm looking for. V naught is 0 because that's in the y direction. Acceleration is negative g t squared. So that would be delta y is equal to negative 1/2 g d squared over v naught x squared. All right, we're happy with that. Cool. Now, that's all you need. You just need these two equations. You solve the problem, we're done. Let's go to an advanced style, though. Let me just write these answers up in the corner over here. I've got t is equal to d over v naught x, and delta y equals 1/2, negative 1/2 g d squared over v naught x squared. You know, another thing I want to figure out is, in the vertical direction, this thing had about 0.3 seconds to fly there. How much velocity did it gain in the vertical direction? Because gravity is pulling it down. So it starts off with a 0 velocity, but then it increases because gravity has had 0.3 seconds to act on it. So one way to solve that, and that's pretty straightforward as well. V final y is equal to V final y is equal to V initial plus AT. That's just the first equation. V initial in the y direction was 0, and so you have V final y is equal to negative g times d over v naught x. All right, I'm going to write that down over here. Because I kind of want to discuss with you something that I think is harder. This, obviously, this topic right here is actually not what I expected you to do on a high school exam. But one of you did it, and so it really excited me to think that you guys thought about this information. The question that you kind of posed was, you know that velocity is equal to 105.96, I think that's what it was, 105.96 miles per hour. I guess the question that you ask is that mean that it left his hand at 105.96 miles per hour, or the guy caught it at 105.96 miles per hour? Because those velocities are actually different. They're very little different, I admit to you, because really you got the initial velocity and then you got this thing right here. It's almost all in the x direction, but there is a little bit in the y direction. So technically, if you measured it over here, then 105.96 miles per hour could be this. It could be this thing right here. V, I'm just going to call it V final, without a subscript x or y. That could be 105.96, which would change this answer and this answer and this answer. So, you know, like if you were to assume that the radar gun measured it right over here, then all of these answers would be correct and you would be good, and that would be about what I expect a high school kid to do. But if you were to assume that the radar gun was over here, then it gets a lot more complicated, and I'm going to go through it and show it to you since this is just the solution. But I don't expect you to do this analysis, but I do want you to start thinking about it. So why don't you come on a ride with me? I know that this is pretty simple from the Pythagorean theorem. This says that V final squared equals V initial squared plus V final y squared. Now, the reason why I don't have a V final x and a V not x is because I'm not including air resistance. If I included air resistance, this problem would get a lot harder. And that would be even beyond what I think a college kid would do. I think that would probably be more of a graduate level or a junior or senior in college studying physics. Let's see. I know that my V final y is actually that, so that's V final squared is equal to V naught x squared plus G squared D squared over V naught x squared. And I also know that, well, I want to solve for V naught x, so I'm going to get rid of that fraction right there. And I'll have V naught x squared V final squared equals V naught x squared plus G squared D squared. I'm going to take every, oops, that's a fourth power, because I'm multiplying this V naught x squared times that V naught x squared, and you get V naught x to the fourth power. What I'm going to do is I'm going to take everything over to one side. So I'll take this one over to that side, and I'll have V naught x to the fourth power minus V final squared V naught x squared plus G squared D squared equals to 0. All right. How do I hit that? Well, that's pretty simple. That's the quadratic equation. If x is equal to, and when I'm talking about x, I'm not talking about like this kind of x. I'm talking about like the x from ax squared plus bx plus c. That x is equal to v naught x squared. Then I can just use the straight up quadratic equation. All right, here we go. Quadratic equation on this thing would be v naught x squared is equal to negative this thing, so that's actually positive v final squared, plus or minus the square root of this thing squared, so that would be v final to the fourth power minus 4 times 1 times g squared d squared, so that would be 4 g squared d squared all over 2 times 1. And so the v final would actually be the square root of this, or the v initial would be the square root of this. Now, if your v final to the fourth power is much, much bigger, all right, so this is technically the correct answer. That's the velocity that he threw it at. That's the velocity at which it left his hand at. So then technically you would use this velocity for here and you would get a new time. You would also use this velocity for here and you would get a new fall. And you would use this velocity for here and you would get a new v final y. So in the previous problem, we just assumed that this v naught x is the same as that v final x. Well, and that's true. But in the previous problem, we just assumed that this v final was the same as this v final x. But you can see right here that it's a little bit longer. The v final is a little bit longer than v final x. So we assumed that this v final y was 0, essentially. Now, one way you can kind of analyze this is if you say, well, what happens if v final is much bigger than 4g squared d squared? Actually, I'm going to do a v final 4 is much bigger than 4g squared d squared. I'm saying that this thing dominates that thing. Which, if you're throwing something at 105.96 miles per hour, and then you bring that to the 4th power, that's going to be way bigger than like 4 times 10, or maybe 32 squared times the distance squared. No, that thing is way bigger. No, not, I mean, it's significantly bigger. It's bigger enough. So that's not even that bad of an assumption to make. If that were the case, then essentially this thing would dominate this thing, and you can kind of just get rid of this last part because it's so small in comparison to this. If that were the case, then I would have v final squared plus or minus the square root of v final to the 4th power minus 0 all over 2. Essentially, I would have nothing there. So this would be v final squared plus or minus the square root of v final to the 4th power, which is just v final squared over 2. So it's telling me if I use the positive, if I use the plus, then it would be 2v final squared. I need to take the square root of this whole thing because it's all under a big square root over 2 square root. This is v naught x is equal to v final. That's a good thing because what it's saying is that if we're assuming that this velocity is much bigger than that, then essentially you can go back to using what we saw in the high school level, the very first version. We can go back to assuming that v final is the same as v initial x. Now, if you want to be super accurate, technically you would have to use this thing right here, and you would plug it all in. But this is kind of interesting because it's telling us how, at what limit can we take it where we don't have to consider this thing, where we can only kind of do it the, I don't want to say dumb way, because this is obviously not dumb. I mean, this thing looks a lot more complicated than being dumb, but where we can do it the very simple, maybe basic way, as compared to like the more complicated way. Shoots, bro, up out.